Okay, hello ladies and gentlemen. Right, well, discounting water, 50% of you is made of protein. But what are proteins? Well, proteins are macromolecules, that's large molecules, made of subunits called amino acids. Now, in nature, there are 20 amino acids, as demonstrated here, and we biochemists give them a one-letter code. Now, each amino acid has its own character. Some of them are positive, some of them are negative, and some of them have a neutral charge. Some of them like to be in a water environment, and some of them don't. Some have bulky side chains attached, and some are smaller. And these characters determine the function and the structure of the protein the amino acids reside in. Now, amino acids are in a linear sequence in the protein. And if you think of amino acids are letters, the protein is like a word. And so this linear sequence creates a peptide. This is just a note to myself to smile during the presentation. So this sequence is coded for in the DNA, and if you think of the DNA as a foreign language, this must be translated into the language of amino acids in order to get a protein. With 20 amino acids, this allows for a large variation in function and structure, and this is what bacteria uses. However, in more complex organisms, we have an extra level of complexity. These are modifications that occur after this translation from DNA into the amino acid language. And, not surprisingly, these are called post-translational modifications. I'll give you some examples. 2 C amino acids can join via a bridge, which I will illustrate with this pipe cleaner. And this bridge is important in protein structure. Another modification can be the additions of acidic groups. So all amino acids have an acidic group attached. However, the addition of another acidic group, demonstrated by the small pipe cleaner, can control the addition of metals, such as calcium, to the amino acid. And this is important in proteins that are involved in blood clotting. Modifications can be as simple as just the addition of sugar, as demonstrated by the sachet I saw from Starbucks earlier. But not all of these modifications are beneficial, and in some diseases, detrimental post-translation modifications can be a cause. I look at one of these in my PhD, specifically the addition of oxygen, demonstrated here, to the amino acid histine, and this is in a protein called amyloid beta. If you imagine this pipe cleaner as the amyloid beta protein, in Alzheimer's, 5 of these join together and they self-associate. They stick together and twist into a fibre, like so. And this is a toxic species in disease. However, with the addition of oxygen at the 3 histidines in the sequence, here, here, and here, this can interfere with the self-association of the 2 fibres and hence affect this aggregating process. Therefore, by studying addition of oxygen to histidine, we hope to further understand the pathology of Alzheimer's disease. That's it. Thank you.